to resynthesize ATP? Well, fundamentally, this is the ATP reaction. So we start off with ATP, which is just stored in the muscle cells. We're dealing mostly with muscle cells within the course of this lecture. So the ATP is stored in the muscle cells. In the presence of the enzyme ATPase, the ATP is split, and what we end up with is ADP plus PI plus energy. So what happens is that if we add ATP, the bit that's perhaps missing here, I suppose, is ATP plus water. So ATP plus water, it's the simplest chemical reaction. In the presence of the ATPase, which is an enzyme, and I'll explain about enzymes in a moment, creates this splitting of ATP. What it does is it cleaves, that is, it drops one of the phosphate molecules from ATP. ATP is quite simply an adenosine molecule with 3 phosphate molecules attached. By cleaving off a single phosphate molecule, we end up with adenosine diphosphate, that is adenosine plus 2 phosphate molecules. And we have this free phosphate floating around. And this then releases energy. But notice that the reaction is reversible. So if we take the phosphate and add it back to ADP, we'll end up with ATP. And we'll explain about how that works a bit later. But the issue that you've got is quite simply this. We've got ATP stores of around about 20 to 25 millimoles per kilogram. And we can get a peak turnover rate of about 15 millimoles per kilogram per decimeter per second. It's a slightly different way of expressing the units to what we saw earlier on. But the fundamental thing is this. What that equates to in terms of the stores, 20 to 25 millimoles per kilogram, is we've got enough ATP for probably a single maximal muscular contraction. So a single maximal muscular contraction. We've got about 80 grams of stored ATP in your bodies. But we need ATP in order for a muscle to lengthen and shorten. It's the currency that muscles use. The key thing is that the ATP is split, and that allows the muscle to lengthen and shorten. Now, the problem that you've got, in order for that to happen, is if all we've got is a limited store for a single muscular contraction, that's no good. That means we can do one muscle contraction and nothing else. We need to be able to resynthesize ATP, and that is where all those processes we've been hinting at previously start to come in. So let's think about the onset of exercise. Let's imagine we're dealing with something like a sprint. So we need the energy to be derived very quickly, but the next immediate store is our phosphocreatine that we've already looked at. So we know that intramuscular stores of PCR, which are located in the cytosol of the cell, we have around about 80 millimoles per kilogram. That's the capacity. And during maximal work, the degradation follows an exponential decay with maximal turnover rates of about 9 millimoles per kilogram per decimeter per second. So don't worry that the numbers look different, but the units are slightly different in that we've got now decimeters within these. So you get near depletion within around about 10 seconds. So here's the reaction. Remember that the key to understanding is this. We're trying to resynthesize ATP. What we're left with after the splitting of ATP is ADP. We cannot simply just add phosphate back to that. The only way that the phosphate can be added back is actually under conditions of what we may refer to as rest and recovery. That is where the metabolic rate has slowed down. But if we're exercising at a high intensity, the metabolic rate, the rate at which we derive the energy, is incredibly fast. So we cannot simply add phosphate back onto the ADP. So what happens is we have this phosphocreatine reserve, again, which is sitting within the cytosol of the cell. The PCR is added, or adds itself to the ADP. Also adds to this, we add a hydrogen ion. Don't worry about the hydrogen ions per se. And what that does is it gives us ATP. So what we do is we take a phosphate molecule from PCR. Now the fundamental thing here is to understand that it's not a case of simply just donating one. The phosphocreatine pool has got lots and lots of phosphate molecules attached to it. So what we're doing is we're cleaving a phosphate molecule each time. So remember that we want to add a phosphate molecule to ADP, and by doing that we get back to ATP, and we have creatine. All the creatine is saying is that we've donated a phosphate molecule from PCR. Once we've got the ATP goes back into this reaction, it's added to water in the presence of ATPase, we split the molecule, we get ADP, PI and energy. So this process is driven by the enzyme creatine kinase. Now the enzymes are fundamentally important to substrate level metabolism. The enzymes never appear in the final outcome of any reaction, they just merely drive the reaction. And that's really important to appreciate, they drive the reaction. We know that it's an enzyme because it's an ase. So if you're wondering what something is, if it's got an ase on the end of it, it's almost certainly going to be an enzyme. So we've already talked about lactate dehydrogenase, we've talked about creatine kinase, we've already referred to ATP, ase, they're all enzymes. So it drives this reaction. Now what we understand is that we can increase creatine kinase through training. So if we do high intensity training, it will increase this. What the enzyme does is it drives the reaction rate. So the rate is fundamentally, so this is the power that we're referring to, is fundamentally driven by the abundance of the enzyme. It is not driven by the abundance of the substrate. The substrate, that is in this case the PCR, reflects quite simply the capacity that we have for that as a substrate. So where it says here we've got around 80 millimoles per kilogram, that's of just the PCR. The 9 millimoles per kilogram per decimeter per second is governed primarily by the amount of this creatine kinase that we've got, the enzyme. The enzymes themselves, though, are affected by a number of key things. They are very sensitive to temperature. So if the cell temperature is high, then the rate at which these reactions, particularly if it's very high, the rate of these reactions slows down. What we know though, at low temperatures they slow down as well. So there is kind of an optimal range, or optimal temperature range under which these reactions work. And as kind of the temperature rises, the rate of the reaction increases until you get to this point where the temperature is too high. We also know that they're affected by the pH of the cell. If the cell is too acidic, that is, we've got maybe an increase in hydrogen ions, which are associated with lactate. If we have an increase in those, that actually starts to lead to what we call a deamination of the enzyme. The enzyme is firstly slows down the rate at which the enzyme works, but also if the cell becomes too acidic, it can actually cause the enzyme itself to break down, which therefore slows down the rate at which any, not just this reaction, but the rate at which any of these chemical reactions can take place. So if we go back to our analogy of a 400-meter runner, and we're saying that they're going to run the 400 meters in, let's say, 45 seconds, two things we've seen two really important hints. First hint is here. One, we can see that we get near depletion within about 10 seconds of going flat out. The second hint we saw was on a previous slide. So if we just go back through the slides, what you'll see is on this slide here, notice that after about 6 seconds, you get quite a significant decline in the PCR, and we start to then get a reliance on other substrates contributing. Remember that we're still trying to maintain the leg speed of our 400-meter runner, but the reaction is starting to slow because we've got less PCR. So this is where glycolysis comes in. So here, the same thing that we've already been looking at, this is substrate level glycolysis, which ends in the formation of lactate. So here you've got glycogen plus 3 ADP plus 3 PI gives us 3 ATP plus 2 lactate plus 2 hydrogen ions. Don't necessarily worry about the chemical reaction. What I want you to worry about is what the writing is telling you at the top. ATP production for substrate glycolysis is activated at the onset of exercise, so fundamentally reinforcing what we've already seen, that no energy pathway works independently of another one. At the onset of exercise, it reaches a peak of around about 6 to 9 millimoles per kilogram per decimeter per second after about 5 seconds. But we know that the capacity for this is far greater. We can sustain this, we've already talked about, for about 60 to 90 seconds, whereas we've got near depletion of this within 10 seconds. The turnover rate for the ATP PCR is around 9 millimoles per kilogram per decimeter per second. Here, the absolute peak is 9, but that isn't maintained. And in fact, we're looking at around about 6 millimoles per kilogram per decimeter per second. And it reached that after about 5 to 6 seconds. So what we know from glycolysis is we get between 3 to 4 ATP. It depends on where the process starts in terms of how many ATP we yield from this, whether we start with glucose or glycogen. So the key to understanding though is, although we produce 4, the net gain would be 2 if we started with glucose. The reason for that is it costs us 2 ATP. So we actually use ATP in the process of yielding ATP from glycolysis. If we start with glycogen, it only costs us 1 ATP. So the net gain is 3 ATP. So it's an interesting process that we use ATP to form ATP in this metabolic process. But we end up with, as you can see, with the production of lactate and hydrogenase. If we look at aerobic metabolism, it's a much more complicated process, because fundamentally here what you'll notice is that there's a lot of other factors at play in terms of we're using glucose C612O6, but there's a lot of CO2 being produced in this process. But the key here is anywhere between 36 and 38 ATP. Again, it depends on where the process starts, whether it starts with glucose or glycogen. But that's 38, let's take it here, which is 38 ATP compared to just 3 ATP. So the amount of energy you can derive from substrate level metabolism of glucose aerobically is over 10 times more per molecule of glucose than you would derive anaerobically. But the rate at which you derive this is far, far slower. So we've got a rate here of about 1.32 millimoles per kilogram per decimeter per second compared to 6 to 9 millimoles. Let's take it, the difference there is substantial, isn't it? It's almost, it's bordering on maybe 1/9 the rate at which you derive the energy anaerobically. And that is why, fundamentally, we start to see much, much slower running speeds or exercising speeds aerobically compared to anaerobically. You cannot derive the energy fast enough under aerobic conditions compared to anaerobic conditions. And so what we get is a very, very unique relationship.